In today's lecture, we will continue the topic of the previous lecture, elements of mathematical statistics. Let me remind you that we have focused on two main methods for studying statistical aggregates, IDS large data sets. This is a solid method and a selective method. The selective method, in particular, is considered the main method of studying statistical aggregates. It consists in being able to judge the numerical characteristics of the general population by the properties of the sample, which is inaccessible for studying the general population, or is very large, or requires some huge investments to obtain objective information. In general, one way or another, in statistics, it is most often resorted to a selective method of studying certain objects. Objects, characteristics of these objects in medicine, in particular, the selective method is the main method of study. In other words, it studies some part of, let's say, patients, some part of a specially selected part is evaluated, and the data from this sample population is transferred to all other patients who are characterized by this or that trait, according to which they were selected. Each object from the general population falls into the sample when two conditions are met. The first condition for getting into the sample population is typicality, and very briefly, in my opinion, I talked about it in a previous lecture. Typicality, which means that the sample should include those objects that are typical, that is, equivalent for the entire general population. The objectivity of the sample means, first of all, a random choice, an option when making a sample. That is a sample population variance, that is, objects fall, most importantly, randomly, not in a subjective way. Selection from the general population to the sample can be carried out by various methods. These methods are discussed in more detail in practical classes. Well, it can be, for example, the lottery method, the drawing method, or previously used, for example, the method of random tables. Currently, for example, in medical research, the objectivity of the sample is checked, so to speak, by subjective methods. In other words, despite the fact that very few objects often get to the researcher in medical research to check and convince others that each object from the general population falls randomly, this is one of the tasks of the researcher. After the selection is made from the general population to the sample, calculations are started. That is, quantitative estimates are started. And these quantitative estimates, if we try to type them, currently there are three. This is the so-called method, a point method of estimation, in which, for example, the sample mean of the sample variance and the mean square deviation are calculated. This is an interval method of estimation, in which, in addition to the average, the confidence interval in which the sample average will fall is calculated. And this is a comparative method by which two, for example, sample populations obtained from one general population are compared and then evaluated using various criteria. Criteria, for example, the student criterion, the Fisher criterion, and so on. We're going to go straight to the next one now, to the next presentation, so as not to distort it anymore.
So, we begin quantitative to study quantitative estimates of the general population according to the sample with a point estimate.
Here is the point estimate you had written, assumes the calculation of the average value, assumes the finding of the average variance, and the mean square deviation. Write down the sample characteristics, and remember, of course, they are approximate characteristics. In other words, all the estimates that we get using the sample are estimates that will always deviate from the estimates of the general population. That is, no matter how well we have selected variance from the general population, a sample one is always allowed when the correspondence is incomplete and an error is most often observed. Therefore, the sample characteristics are approximate characteristics. The sample average characteristic is denoted by the letter and the average and is called, and can more accurately be calculated as an arithmetic mean. Here is the calculation formula, according to which the sample average or arithmetic mean x average is calculated. Well, all the options are added up and divided by the number of terms. The sample variance can be calculated in exactly the same way as the variance the formula that we wrote down in the last lesson can be calculated using this formula will be approximately the same. And finally, the sample mean square deviation. This is still the same square root of the variance. Sample characteristics. As a rule, general characteristics are constant values. Of course, they are unknown because the voluminous general population does not always provide such an opportunity to study it in its entirety. Well, except for the methods of continuous research there, such as the census, the study of rare diseases, and so on. But in any case, the characteristics of the general population are constant characteristics. Sample characteristics are variables. These are quantities that vary around the general average value. In other words, it may be a little more, a little less, but the size of this little bit is included in the definition of this size. This deviation is included in the tasks of the selective method. That is, The sample method, first of all, under the number 1, please note, should determine the reliability of transferring the results of a sample study to the general population. This is the first task that the selective method faces, and the second is taking into account the conditions under which the sample most fully represents the general population. That is, compliance with just the conditions of typicality and the conditions of objectivity. Here are some more tasks that are set before the selective method. In other words, I repeat, no matter how well we select options from the general population into the sample, we know in advance that we will make a mistake. In other words, no matter how thoroughly, scrupulously we approach obtaining a sample population, the sample method itself already carries some errors. On this slide, the characteristics of the sample population are compared with the characteristics of the general population. Well, I can notice that it is sometimes possible to write a mathematical expectation in place of the general population. In other words, the average value for the entire population in statistics can be denoted as a mathematical expectation. We pointed out in the last lecture that mathematical expectation is nothing but a measure of the average for any distribution. So here's calculating the sample average and the average. The X line indicates it. If we are confident in our choice, in our calculations, we transfer the sample average to the general average. That is, we will select 10 people from, well, maybe I don't know, there are millions of patients suffering from various diseases. Let's study these 10 and say that the indicator, let's say some biochemical indicator of blood for the entire data set, that is, for the entire general population, is approximately as much as the sample average shows us. Similarly, it comes from variance. The variance is considered to be selective and projected, IDS transferred to the general population. The mean square deviation is sampled by the mean square deviation of the entire general population. The error of the arithmetic mean, of course, depends on the volume of the sample population. In other words, there is such a duality here. The fewer objects for research, the faster, for example, the research proceeds, the less labor it requires to conduct this research. But, of course, we lose accuracy at the same time. In other words, the smaller the sample size, the fewer objects got there, the less accurate the assessment will be of the general population, according to this sample characteristic. To increase the sample size, doctors sometimes simply do not have the opportunities. In other words, there is, let's say, no consent of patients to conduct a particular study. There are no suitable objects at all. There are not enough suitable objects in a sufficiently large number. We have to work with what we have. Therefore, an increase in the sample size, of course, would lead to a more correct assessment of the general population. But on the other hand, if this is not possible, we have to resort to other methods of minimization. Deviations. Well, we should not even say deviations, but this uncertainty, our uncertainty, that we evaluate the general population from the sample. So, here are the basic formulas for calculating an ingenious formula for finding an ingenious parameter in general. A parameter that does not possess all the information of the general population, nevertheless shows the accuracy of the estimate based on a sample of this general population. This value is called the arithmetic mean error or representativeness error. This value is denoted by the letter m. Now I'm going to try to enlarge why it turned out so badly for me. Miss Small with the index x is medium. Well, that is, here they are. These errors are indicated 4 times on this slide. The letter m indicates an error, and the index x with a dash says that this error is related to the sample average. That is, the error of the arithmetic mean, the sample arithmetic mean. The arithmetic mean error is calculated using different formulas in cases where the sample size differs. If the sample size is sufficient, that is, if the number of objects studied by the sample population is more than 30, then the arithmetic mean error is calculated according to the formula, which is combined with a blue frame. So, the error of the arithmetic mean, please note, depends on the value of the arithmetic mean, or rather on the scatter of values. Between each value of the arithmetic mean, between each value of the sample and its arithmetic mean. In other words, the further apart the quantitative characteristics of the sample objects are, the greater the arithmetic mean error will be. In other words, the more heterogeneous the sample is, the greater the error, the less confidence we can transfer the data of the sample population to the general population. In a sample of more than 30 objects in the denominator, the calculation formula, look, is n squared. N is the number of variants, IDS the sample size. The error is arithmetic mean for large samples, or for just samples, you can still calculate it using the lower formula. The formula that contains 2 parameters is the mean square deviation. Here it is sigma squared divided by h by the sample size. Well, this is if, for example, the standard deviation is known, or you can use it in some way with the help of transformations. Most often, doctors use a formula indicated by a yellow frame, that is, the so-called arithmetic mean error, for small samples. In other words, circle this formula thicker and remember. It is according to this formula that we will have to consider the task that will be presented in your control work, because, I repeat, most often we have to deal with small samples. A small sample is a sample that does not exceed 30 variants, the volume of which does not exceed 30 objects, or 30 quantities that make up this sample. Well, just like the previous formula, the error of the arithmetic mean for a small sample depends on the scatter of values. In other words, the more these differences are squared and then summed up, the greater the error of the arithmetic mean will be. But, of course, the arithmetic mean error will decrease when the volume increases. Sample size. That is, it's one thing when we, let's say, multiply 30 by 29, and another thing when we, let's say, multiply 5 by 4. It will be different denominator sizes, and of course, it will be a different error. The error of the mean representativeness error, or the error of the arithmetic mean, can also be calculated for small samples using the mean square deviation, but only if the mean square deviation is known. In the denominator of this calculation formula, but also in contrast to the formula for just samples, the value is indicated even less than in this formula. That is, using this comparison, it can be seen that the arithmetic mean error for small samples is an even greater value, since the denominator decreases here. And in this case, in the first case, in the case of the upper formula, in the case of the second formula, here are some wonderful formulas that you will have to work with. As I have already said, they allow us to evaluate the accuracy of transferring sample data to the general population without having full information about this very general population. The fact that with a decrease in the sample size, the accuracy of estimating the general population decreases, as a matter of fact, can be seen from the calculation formula itself. Increasing more precisely, well, yes, increasing the accuracy of the assessment, selective assessment by increasing the volume, is sometimes an impossible task. Therefore, we have to take it for granted. Here is the order of solving the problem by a small sample method. This is the name of this method. This is the very method that you will have to demonstrate when solving the task of a control work on statistics. In each variant, each of you will have your own version. I mean, the group will offer its own set of data in a practical lesson. That is, someone will come across, let's say, 29 different values of blood pressure collected under certain conditions, someone's pulse purity, someone's height, someone's weight, and so on. In other words, it will be necessary to work with different values, but the solution scheme, of course, is the same. The scheme assumes, first of all, the separation of data in the table. That is, each of you will have indicated that, according to the sample population, it will be further these enumerations of the x of the first and the second and so on and valuable. So, according to these data, you will need to evaluate the general population according to the available sample values. That is, You will need to find the mathematical expectation. You will need to find the variance, and you will need to find the sigma. These are all general parameters. That is, the general average, the general variance, the general mean square deviation. The table is built in the following parameters. These are 4 columns, an ordinal number, the value of x, that is, all the values that you will transfer here. I have already said, for someone it will be, let's say, the purity of the pulse from the x of the first to the x of the last. For someone it will be the value of growth. In general, no more than 30 values. Well, 30 at most. That is, from the first to the 30th. In the second, well, more precisely, this is the third column of the table. The difference is indicated if the task is considered manually. Usually this column is highlighted, and then a fourth one is added, where this difference is squared. In other words, this difference can be calculated modulo without taking into account the sign of this difference. In other words, less is taken away from a larger value. Well, the calculations are already beginning. That's why we go directly to the scheme for determining the general parameters based on sample data. So, first of all, it is calculated when you get the task to solve the problem of the small sample method. The first thing that will need to be done is to determine the sample size. That is, to calculate simply how many values, different sample values, are represented in your version. Someone who is lucky will have 15, someone who is unlucky will have 30 values. Well, in any case it's not. These are small samples. Next, the second step, find the sample mean, that is, add up all the sample values, divide by the number of terms, find the arithmetic mean. Thus, a sample average will be found for you. Then, having reached point 3, we proceed to filling out the table. That is, the values from the x of the first to the x of the last you have entered. Then you can fill in the third column and the fourth. The value of the third column is the difference between the average that has already been found, and each value. That is, if, let's say, the average height there is 165 and the first x is 160, then the difference, I repeat, by sign is not important. That is, write 5 in the next column, square the 5. Yes, if, well, I repeat again, the average, let's say, is 165 centimeters, and the value of x2 is 170, I don't know, 172 centimeters. Then again, without taking into account the sign, well, it won't be taken into account here. Put 7, then square 7. This column, the fourth column. Then it is summed up, that is, the value of the mean square deviation. I'm sorry, before calculating the mean square deviation, you need to find the arithmetic mean error itself, and the sums of squared deviations are placed in the calculation formula of the error. That is, here it is the sum icon, which means that the entire fourth column will need to be added. Here they are squares, and here it is a deviation, the deviation of each value from the average. Deviations squared, summed will give. I'll be back. Oh. They will give us the value that is indicated in the numerator, in the calculation formula of the arithmetic mean error. That is, by adding up all the values of the fourth column, you will thus get a ready-made numerator for a formula that finds the error of the arithmetic mean for a small sample. It remains to divide by the product of n by n-1 and the error of the arithmetic mean, well, after the root is found, will be determined. After you find the value of the arithmetic mean error, you will need to calculate the mean square deviation.
Sigma.
The mean square deviation is calculated. I'm already afraid to scroll. It is calculated according to this formula in this case. The mean square deviation, denoted by sigma, is expressed from the calculation formula and according to the found value of the arithmetic mean error. Well, of course, the size of this deviation is determined by the known value of h. The found sigma value of the mean square deviation allows us to find the variance. In order to find the variance, it is enough to square sigma. And finally, after calculating the value of the mean variance and the quadratic mean, it remains to make the appropriate entry. On the transfer of the obtained sample data to the general population. To transfer the data to the entire general population means, well, about what we started with when I scrolled back again. When they talked about the disadvantages of the selective method. In other words, here it is a calculated sample average projected on the average of the general population. Here, it is the sample variance projected onto the general variance, the sample mean square deviation onto the general mean square deviation. There are some features that clarify this very transfer. That is, it's not just that we calculated the sample average and then took and recorded that this is the general average. There are additional methods that resemble, well, approximately how, let's say, laboratory work in physics is designed. Surely you did this at school when he writes that the average, when the desired value is written, is found as the average value plus or minus a certain scatter. That is, plus or minus a certain deviation. There is an error. There is an absolute error. Relative error in general is not the point, but the range of values in which the general population can fall is indicated. I repeat, in any case, having found the average sample population, we will find only an approximate, one of the approximate estimates of the general population, because the selection of the sample population from the general population will change slightly, that is, we will change the objects. One of the objects that was selected, we will return the general population. Well, Or we will change it to another. Let's say a person, yes. When determining there I do not know the average weight. Then the selective parameters will immediately change. That is, for example, the average value will change immediately. Therefore, most often we get a certain range of values that should fall into the general population. Well, in the problem, after you calculate the average, you will need to write down the error of the arithmetic mean sigma and the variance, well, with some standard way that the general average approximately equals the sample value of the average. The general variance equals the variance that you found. General sigma is approximately what you calculated for this task. So, for, as I have already said, greater confidence that the sample estimate will be reliable, the sample estimate obtained when transferred to the general population will be reliable. Use intervals. In other words, they set a certain interval in which the general average can fall, and, well, great confidence is achieved that this is really the interval in which the general average will fall. And the average in this case with a dash is a sample average. In other words, to determine the width of the interval, you need to know what the sample average will be equal to, and you will need to know the size of this delta, that is, the size of the defined width of the interval. The lower bound of the so-called confidence interval is set as a sample mean minus delta, and the upper bound is defined as the mean plus delta, of course. In general, the interval is called the confidence interval. To determine the exact values of this confidence interval, of course, you need to know what this delta equals. How can I find the size of this interval? In other words, we proceed to the second method of estimating the general population from sample data, to the interval method of estimation. The task of interval estimation is to use the sample data and a given confidence probability to find the accuracy of finding or hitting the parameters of the general population in a certain interval found. So I'll go back to the previous slide again because a new term appears. Here's a look. According to the sample data, yes, we make an interval estimate and a given confidence probability. This very confidence probability means that there is an additional condition, an additional requirement, that needs to be taken into account when calculating in the interval estimation. Confidence probabilities are probabilities sufficient for a confident judgment about the general parameters. These confidence probabilities are denoted by the letters p large with the alpha index. In statistics, it is customary to use three values as confidence probabilities. Look, all three values are values close to 1. That is, the probabilities of these random events must be assumed. They are close to reliable events, that is, to events whose probability is equal to 1. So the first probability is 0.95 hundredths, the second one is 0.99 hundredths, well, 999 thousandths. Confidence probabilities are specified, well, based on the requirements, based on what objects you have to work with. They are specified at the initial stage of the study. That is, if one error out of 20 experiments is allowed in the experiment, then it is possible and necessary to take the first confidence probability. If one deviation is allowed for 100 experiments, then the second probability is used. And finally, if it is taken, if the highest requirements are placed on the reliability of the results, then the third probability is chosen. .999 thousandths. It would be nice if only the third probability was used in biomedical research. Yes, when one deviation per thousand would be allowed. Well, I repeat, this is quite difficult, so in your calculations, you can pay attention to the fact that they most often use the first value of probability 0 as much as 95 hundredths. That is, initially, at the very beginning of the experiment, we say that yes, we assume that once out of 20, we will make a mistake. That is, one patient out of 20 medication will not help. There will be some other effects. Next, instead of confidence probability, well, along with confidence probability, doctors use the concept of significance level. So, I see we should already have a break according to plan. Let's take a little break. We stopped at the fact that instead of confidence probability, the concept of significance level is often used in medicine. This value is denoted by the letter alpha. It cannot be said that this value is the opposite of the confidence probability, but in meaning, in fact, it is calculated and shows the opposite value. That is, if the confidence probability is a value close to 1, and the greater it is, look at the previous slide. The greater the confidence probability, the closer it is to 1, the more accurate our estimate of the general population is. For alpha, for the level of significance, so to speak, the requirements or the desire are the opposite. In other words, the significance level shows the probability, that the found estimate will be erroneous. In other words, this is the probability of an error. The probability, on the contrary, of not falling into the interval, of going beyond the interval. That's why the lower the alpha, the more accurate, the more reliable the sample estimate is the assessment of the general population based on sample data. Here, well, the standard designation, I have already said, of the significance level is the letter alpha. In order to determine how large the spread of values is, this delta is calculated to determine the boundaries of the interval. The width of the interval is proportional to t, the so-called normalized distribution, and the error of the arithmetic mean. The error is arithmetic mean, but this is the value that you will count in the control work. This is what is calculated according to the scheme, but t is selected based again on the requirements for the experiment. That is, if the first value of the confidence probability 0.95 is chosen as the confidence probability, and let me remind you, one error out of 20 is allowed, then 1 whole 96 hundredths is taken to determine the size of the interval. In other words, the error is multiplied by such a coefficient, and the more confidence probability is chosen, the wider the coefficient becomes. Look, for a probability of 0 as much as 999 thousandths, the width of the interval is already proportional to the coefficient 329. These values are delta, well, respectively, taking into account the confidence probability, taking into account the value t of the renormalized deviation. That's how it should be interpreted. If the value is distributed according to a normal law, yes, that is, if this symmetric distribution is observed, then for the first value of the confidence probability, for the first t, we can say that 5% of the values of the random variable will remain outside this interval. In other words, we will extend the sample data to the general population, and we can be sure that we are right for 95% of cases. But 5% of the cases, they remain outside the interval. In other words, they do not fall within the framework that we have defined for the first level of significance. In the case when the second confidence probability is taken, it will mean that we will leave 1% of the values outside of our interval in the general population. Well, for example, we will be convinced in advance that this method of treatment will not affect 1% of the patient. Well, in the case of the third level of significance, 0.1% of the values of the general population remains outside the boundaries of the interval. The next way that statisticians use is not a method, but a method is a group of comparative methods. Sometimes a group of these methods is called simply comparative statistics. Comparative statistics are based on the calculation of special criteria. They are named most often by the developer's last name. Here is the essence of the comparative evaluation method. In a number of experiments, the result is evaluated using several samples. In other words, the same development of a new drug. There is a new vaccine, new methods of treatment, and so on. These results are evaluated precisely with the help of comparative statistics. With the help of one, and sometimes with the help of several criteria of difference. Well, here is the most typical, maybe the most obvious criterion of difference. This is the so-called student criterion. This is a criterion that compares the average value in normally distributed samples. That is, the averages of the first sample with the average of the second sample. Well, for what and how it compares, a little later on examples. In the case when, well, for example, the value is not distributed in accordance with a normal law, or in the case when this value is not represented by the non-distribution of random variables, but, well, it is not a quantitative assessment, that is, it can be ranks yes, when I do not know there the degree of, for example, a bird is estimated there by the number 1, number 2, number 3, or just yes, no. That is, there is redness, there is no redness. In such cases, another criterion is often used, the so-called chi-square criterion. I pointed out that it compares samples obtained on the basis of other scales. In other words, it is not necessary to compare the averages obtained as a calculation of arithmetic averages for quantitative estimates.
Here.
There is a symptom, there is no symptom. That is, yes, no, 0, 1. In such cases, the criterion of difference, called the chi-square criterion, is considered. Well, sometimes in statistics, the average value of samples may coincide. In other words, we recruited two groups of people for the experiment, conducted experiments. It turned out that the average value in one experiment and the average value in another experiment coincide, but there are some obvious deviations in the scatter. In other words, it's one thing when we get, relatively speaking, the desired result, that is, close to some value required for the relative norm, but in one group, these will be dense values distributed around this norm, and in the other group, despite the fact that the average also fell by the same amount, the spread will be large. That is, there will be large deviations far from the increasing values relative to the average. In such cases, another criterion of distinction is used, which is called the Fisher criterion. So the full set of criteria is not limited to this. Of course, there are a lot more of them than I indicated. Well, here are the most typical criteria. The criteria of a student. We will now take a little more detail. The student's criteria are further subdivided into the so-called two-elimination criterion and the paired criterion. Two harvest samples are used when the hypothesis of equality of the averages of two independent unrelated samples is directly tested. This is the most typical case when, let's say, the effectiveness of a new drug is being considered. The experimental control group is selected in this case, yes, that is, the experimental group that takes the drug, and the control group that either takes a placebo or is treated there according to some old proven method. That's the number of people in these groups. Of course, it can be different. In other words, it will be the same in some exceptional case. For such cases, they use the students to harvest criterion. Well, the students' paired criteria are used to test hypotheses when working with the same group. For example, they take a group of people and take measurements of some parameters before exposure to some factor, I do not know there, by electromagnetic radiation, and then after exposure. These are the so-called criteria, paired criteria for dependent samples of related ones. Well, that is, when the same group participates in an experiment, let's say before exposure, after exposure, then a slightly different formula is used to find the student's criterion. So, well, now we are going to describe this formula, and I think that today's lecture will end with a rather complex and voluminous number of formulas and material in general. So, the criterion of the student, the criterion of the reliability of the difference. Returning to the previous slide, let me remind you that we are going to talk about two sample criteria for the case when there are two different groups of people. When it is possible to find the average value for the first group, let's say for the control group and for the experimental group. The group that participated in the experiment there took on some kind of impact and thus allowed to confirm or refute the hypothesis. And the hypothesis is that when we introduce any drug, we assume that it will be effective. So, if there is a sufficient difference between the average value in the control group and the average value in the experimental group, this is not enough to judge the effectiveness of this drug. It is necessary that the condition is met. Look, the effectiveness of a new technique or a new tool will be recognized, as it were, statistically reliably when the calculated criterion for the reliability of the difference exceeds, well, some tabular value of the student's criterion. I look at the table that allows you to calculate, find the value of the student's criterion. Now it's all visible in the program, or it's set initially. So, in order to find the criteria for the reliability of the difference, in our case, there is an average value for the first sample. There is a value for the second sample. There is a difference between them. And this difference is divided by the square root of the sum of the squares of the arithmetic mean errors. That is, m with index x is the average. These are the errors of the arithmetic mean for the first sample. Here is the index x is the first, and for the second sample with index x is the second. In other words, the more errors there are, and you see, One error, let's say only for the first sample, can affect the entire calculated formula of the criterion for the reliability of the difference. In other words, if there is too much variation in the first sample, then this may affect the obtained calculations of the experiment as a whole. For example, for the same example with a new drug, yes, when the first control group did not receive this drug, was treated according to the old methods, and the second experimental group or experimentally received drugs, and we got a certain spread of averages, then further comparison allows us to conclude about the reliability, statistical reliability of this difference, and as a consequence, the effectiveness or inefficiency of a new technique, a new drug. That is, if the differences between the samples are sufficient. In other words, if the criterion calculated is greater than the standard criterion, then the statistical difference, a reliable statistical difference, suggests that the drug really shifted this parameter in the right direction. That is, it really lowered, say, blood pressure significantly compared to placebo or compared to the first, compared with the old method of treating this ailment. That's if the criterion for the reliability of the difference, on the contrary, is less than the standard criterion. That is, if there is not enough difference, or if it is large, a large spread of the first sample in the second sample. Well, the statistical difference is not confirmed. They talk about the inefficiency of the drug, about the statistical, how to say the unreliability of the difference between the averages. There is always a difference between the averages, since you have to deal most often with living objects. You always get the difference between the averages. That is, even if the drug is really ineffective, people still have different measurement situations. During even measurements can be different, and therefore, their averages for the first sample and the average for the second sample always differ. Here, but this difference is not always statistically significant. In other words, statistical reliability, the difference between the experimental group and the control group, can be confirmed only by such a comparison. Here, the absence of a difference between the averages is called the null hypothesis, that is, when it is assumed that samples taken from the same general population are not affected. One of these samples, well, more precisely, none of these samples, is exposed to any factor that would have an effect and, for example, reduce blood pressure, their ori pressure. But if there is no statistical difference, then, consequently, this factor had a negligible impact. That is, if this factor is a drug, then this drug is ineffective in this case. This tool does not have the proper effect to obtain a statistical difference. I propose to stop on this difficult issue. You will also have a lecture on the continuation of these comparative methods. If you have any questions right now, I'll ask you. I'm ready to answer. I see that there are no questions. Well, then let's stop there. Thank you for your attention. You can be free.